So now that we've primed the topic of chemical equilibrium, now we can jump into Le Chatelier's principle. What Le Chatelier's principle does is it guides us in predicting the effect various changes in conditions have on the position of equilibrium. So what are we talking about when we're talking about position? We're talking about that arrow, the directionality of that arrow. Are we forming products? Are we forming reactants? Are we forming more products? Are we forming more reactants? Which one is heavily emphasized? It says that if a system at equilibrium is disturbed, the position of equilibrium will shift to minimize the disturbance. So remember, when we start a reaction, we are not at equilibrium. Eventually we get there. This is what this is saying, what Le Chatelier's principle is telling us, is that if something changes, if we have a disturbance, right, we're going to move away from a chemical equilibrium. And once we do, the dynamic of that reaction will change so that we can go back to equilibrium. And we'll talk about the different ways that a reaction can do that. So again, we're going to go back to that population analogy. So when populations of country A and country B are in equilibrium, again, test yourself. What does that mean? Do we have the same amount of people on both sides? Or is the rate at which they're crossing equal? Anyway, so when the populations are at equilibrium, the emigration rates between the two countries are equal, so the populations stay constant. So the answer to that test, right, the populations stay constant, the rates are equal, however, the populations are not equal to one another. When an influx of population enters country B from somewhere outside country A, it disturbs the equilibrium established between those two countries. Notice, why is that the case? Why was the equilibrium changed? I see an equal rate up there. The rate is the same, right? So why are we at a chemical equilibrium? It's because our population changed. The result will be people moving from country B into country A faster than people moving from country A into country B. So notice, we still have people moving. We still have people moving from country A to country B. But since we have more people on this side, this rate is going to become greater for a short period of time until we reach equilibrium again. So if this was a chemical reaction, the reaction would be pushed in that direction. After equilibrium is established, a reactant is added as long as the added reactant is included in the equilibrium constant expression. That is, it's not a solid or a liquid. How will this affect the rate of the forward reaction? How will it affect the rate of the reverse reaction? And how will it affect the value of K? We'll discuss these in the coming slides. So adding a reactant initially increases the rate of the forward reaction, but has no initial effect on the rate of the reverse reaction. Why? Because the reverse reaction currently does not exist. So we're assuming that we were at equilibrium, so we do have a forward and reverse reaction. But again, the change has happened on one side. It hasn't affected the other side yet. So the reaction proceeds to the right until equilibrium is restored. At the new equilibrium position, you will have more of the products than before, less of the non-added reactants than before, and less of the added reactant. But you will not have as little of the reactant as you had before the addition. In other words, the reaction has taken care of that excess. At the new equilibrium position, the concentrations of reactants and products will be such that the value of the equilibrium constant is the same, right? It all goes back to that relationship. After equilibrium is reestablished, a reactant is removed. So we had an addition of reactant, now we have a removal of reactant. How will this affect the rate of the forward reaction? How will it affect the rate of the reverse reaction? How will it affect the value of K? Right? Notice they're all tied to one another. So removing a reactant initially decreases the rate of the forward reaction, but has no initial effect on the rate of the reverse reaction. Again, because it's all based on where that change is implemented. The reaction proceeds to the left until equilibrium is restored. At the new equilibrium position, you will have less of the products than before, more of the non-removed reactants than before and more of the removed reactant. But you will not have as much of the removed reactant as you had before the removal. So in other words, that gap has been filled pretty much, right? So that deficiency has been taken care of. At the new equilibrium position, the concentrations of the reactants and products will be such that at the value of the equilibrium constant remains the same. So this is pretty much how we are going to diagnose chemical equilibrium within a reaction. It all goes back to that chemical equilibrium constant. Is that the same? If it's the same, we're at equilibrium. If it's not the same, we haven't reached that point yet. Adding a reactant will decrease the amounts of the other reactants and increase the amount of the products until a new position of equilibrium is found that has the same equilibrium constant. Removing a product will increase the amounts of the other products and decrease the amounts of the reactants. So in other words, you can use this to drive a reaction to completion. Notice, equilibrium shifts away from the side with added chemicals or toward the side with removed chemicals. Again, this all goes back to that idea of the reaction is trying to get back to normalcy. So if you add an excess amount of species to one side, the reaction is going to want to get rid of that. How is it going to get rid of that? It's going to shift away from it so that excess species can be used up. If we take species away from one side of the reaction, the equilibrium is going to shift towards it. Why? Because it's going to want to replenish what it lost. So this is an example, right? We have our reaction, N2O4 yields 2NO2. When NO2 is added, some of it combines to make N2O4, right? So we're adding more what? We're adding more product, right? So when we're adding more product, some of it combines to make the reactant. So it gets pushed in what direction? It's going to get pushed in this direction, right? Because we want to get rid of that excess. Now notice what happens. We're initially at equilibrium. Then what happens to our concentration of NO2? It spikes, right? How do we know this is NO2? Because this one spiked, right? As a result of that spike, what happens down here? We get shifting of the chemical reaction, right? We get that NO2 forming N2O4. After that's taken care of, what happens? We reach equilibrium again. Now notice, does this equilibrium look the same as this equilibrium? No. We have more pieces to the puzzle now, so it's going to look different. However, notice they're parallel lines, right? So they're not changing. So here we have the opposite. When N2O4 is added, some of it decomposes to make more NO2, right? So again, we have equilibrium here. We're spiking our concentration of N2O4. Therefore, NO2 is going to show the same behavior that N2O4 did before. This is going to go for a while until we reach that equilibrium. And once we get that equilibrium again, we're going to have that constant, the same equilibrium constant. Adding a gaseous reactant increases its partial pressure, causing equilibrium to shift to the right. So now we're talking about pressure. We've talked about reactants, adding and subtracting reactants, adding and subtracting products. Now we're talking about pressure. So increasing its partial pressure increases its concentration. It does not increase the partial pressure of the other gases in the mixture. So in other words, we can talk about partial pressure like we do concentration. However, adding an inert gas to the mixture has no effect on the position of the equilibrium. It does not affect the partial pressures of the gases of the reactant. So we're thinking of partial pressures here as concentrations. Inert gas literally tells you, I don't react, right? It's a species that does not react. Therefore, when we add it, we're not going to be considering it as a concentration or partial pressure. So we're going to consider it as just white noise. Decreasing the volume of the container increases the concentration of all gases in that container. It increases their partial pressures. It does not change the concentrations of the solutions, right? So we're talking about volume here. Volume will have no effect on a concentration, right? But what it will do is it will allow for those species to pretty much expand, right? And now that, of course, depends on what kind of species we're talking about. But if we're talking about gases, right, their partial pressures are going to be increased. If their partial pressures increase, then the total pressure in the container will increase. Again, their concentrations do not change, but the partial pressures do. Now, again, we're talking about a decrease of volume. According to Le Chatelier's principle, the equilibrium would shift to remove that pressure, right? Because we're thinking about pressure as we do concentration. So if we have a decrease in volume, the total pressure is going to decrease. Therefore, we're pretty much going to be pushing the reaction towards the reactants that would generate less partial pressure, right? Because we want to get rid of that extra pressure. After equilibrium is established, the container volume is decreased. So we're given another parameter. Okay, so we reached equilibrium, and now we have an even further decrease in volume. How will it affect the concentration of solids, liquids, solutions, and gases? How will this affect the total pressure of all those species? And how will it affect K? So decreasing the container volume will increase the total pressure. Okay, we know this based on Boyle's law. So volume and pressure have a standard relationship that we are familiar with. If the total pressure increases, the partial pressure of all the gases will also increase. This is Dalton's law. So we're using these two gas laws, right? So Boyle's law tells us that decreasing the container volume will increase the total pressure. Dalton's law tells us that if that total pressure increases, so will those partial pressures. Remember, partial pressures all add up together to give us that total pressure. Because the total pressure increases, the position of the equilibrium will shift to decrease the pressure by removing gas molecules. In other words, shifting to the side with fewer gas molecules. So in other words, we can look at a chemical reaction, see which one has less moles, and therefore know that's going to be the direction it'll be pushed. At the new equilibrium position, the partial pressures of the gaseous reactants and products will be such that the value of the chemical equilibrium constant is the same. Notice this is standard throughout all of our hypothetical scenarios that we're talking about. Now, we're going to shift gears a little bit and look at it pictorially. So volume, right? We have volume here, and we have a source of pressure. So because there are more gas molecules on the reactant side of the reaction, again, what reaction are we talking about? We're talking about the reaction right here. N2 plus 3H2 yields 2NH3. So in this specific case, in our first example, what are we doing? We're increasing pressure. What is the reaction going to want to do? It's going to want to decrease pressure. So what does it do? It tries to get rid of gas molecules. Well, we have 4 moles of gas on this side and 2 moles of gas on this side. So what is it going to do? It's going to push the reaction to the right, so we lose moles of gas. Again, the law of mass conservation still exists. Notice we still have 2 nitrogens on this side, 2 nitrogens on this side, 6 hydrogens on this side, and 6 hydrogens on this side, right? But we're talking about moles here, not losing atoms. Now, what happens if we decrease the pressure? Again, the reaction will always want to go towards equilibrium, right? So here, right, in our first example, what does it do? It tries to get rid of that pressure. Now, in this second example, what is it going to do? It's going to want to pretty much make up for that loss. Again, we have increase in pressure on that side. We lost gas, right? We lost moles. So if the opposite is the case, then what are we going to do? We have 4 moles of gas on this side and 2 moles of gas on that side. We're going to want to go to the left. Why? To increase gas, to therefore increase pressure, right, and account for that decrease. Now we're going to talk about temperature. So we talked about concentration, we talked about pressure, So again, with pressure, remember, we have pressure acting as a concentration, and we also have pressure related to volume. Now we have temperature. Exothermic reactions, we all know what those are. We know what endothermic reactions, right? We're talking about exo means release, therm means heat, so we're releasing energy. Endothermic is going to be absorbing energy. So endothermic reactions tend to feel cool, exothermic reactions tend to feel hot. A great way to apply Le Chatelier's principle to exothermic and endothermic reactions would be by writing heat as either a product or a reactant. Now, in an exothermic reaction, heat would be a product because they release energy, right? So heat's going to be a product of that reaction. Whereas in endothermic reactions, they are taking in, right? They're absorbing energy. Therefore, it's going to be a reactant. So here we have a chemical reaction and we have heat as a product. Therefore, it is an exothermic reaction. So we're treating heat as a product. So if we remove heat, what's going to happen? If we take this system and we cool it down, well, the reaction is going to want to push in that direction. Why? Because it's going to want to make up for that product that we've lost. Adding heat to an exothermic reaction will decrease the concentration of products and increase the concentrations of the reactants. Why? Because remember, heat is a product. If we add a lot of products, what's going to happen? The reaction is going to push away from those products, so not only will heat be used up, but so will the other products. Adding heat to an exothermic reaction will decrease the value of K. It all goes back to these basic fundamentals. What does a decrease in the value of K mean? It means that we have more reactants than we have products. How will decreasing the temperature affect the system? So we talked about how increasing temperature affects the system. How about decreasing? So for an endothermic reaction, heat is a reactant, right? Because remember, in endothermic, heat is going into the system. So now we have heat on this side. So we have what? We have our chemical reaction, we have N2O4, we have NO2, and we have heat being added. If we are to add heat to this reaction, we're to take this system, right? We stick it in the microwave. A microwave is a bad example. Oven, right? We heat it up. What's going to happen? Well, we have a lot of extra or excess reactants. So the reaction is going to push away to get rid of that excess reactant. But as a result, what else happens? So if we're getting rid of heat, we're also going to be getting rid of this species. And we're going to be making more of this species. To what? To achieve equilibrium, to achieve that same equilibrium constant. So in this case, adding heat to an endothermic reaction will increase the value of K. Why? Because an increase in the value of K represents more products than reactants. And here's an example of that reaction. So notice that N2O4 was colorless, NO2 is brown. So when you can just, not even looking at these temperature values right here, we can already assume what's going on here. Well, we have a lot of colorless solution. So we're probably taking heat away. How do I know that? Well, because when I take heat away, the reaction is going to want to replace heat. How does it do it? By using up NO2 and producing more N2O4. What about here? Here we have a lot of brown stuff, right? We have a lot of NO2. What does that tell you? That tells you that heat is being used up to form more NO2, right? So chances are this system is hotter, right? The brown system is going to have more heat associated with it, whereas the colorless tube, the colorless system, is going to have less heat associated with it, more heat leaving the system. So we've talked about how pressure, concentration, volume, temperature, how all these affect equilibrium, right? Now we're going to talk about something that does not affect equilibrium. This is catalyst. So we've talked about catalysts before, right? They provide an alternative or more efficient mechanism by means of what? By means of lowering that activation energy. In this class, catalysts will work for both forward and reverse reactions. So when you dump one in to a vessel, right, it's going to have both catalyze that forward reaction as well as catalyze that reverse reaction. They will also affect them by the same factor. So one, it won't catalyze the forward reaction to a greater extent than the reverse reaction. It'll catalyze them by the same factor. For this reason, they do not affect the position of equilibrium. Because if they're affecting both rates at by the same factor, then it can't push it or pull it away from equilibrium. You are now ready to take the lecture quiz for March 24th.